Alright guys, so this is our video on the first rules of differentiation. And with these rules of differentiation, what we're talking about are basically the shortcuts for taking the derivative, right? Where we're not going to have to use the limit definition of the derivative anymore to take the derivative. We can apply these rules of differentiation and they allow us to take the derivative much faster. And the first rule that we're going to talk about is the power rule. And the power rule says that if we have a function x to some n power, right, where n is a constant, then right here we would say that the derivative of x to the n is going to be n times x to the n minus 1, where basically we're multiplying in front by that power and subtracting 1 in the exponent. Now, because we're using this rule so much, we're going to go through the process of proving this rule, and we're going to use the binomial theorem to do that. So right here, the binomial theorem, remember, says that if we have a binomial, or two terms that are being added or subtracted, that are being raised to some power n, then when we expand out that binomial or multiply it out, we get a polynomial of this form right here, right? And right here, what we're saying with this expanded binomial is that our terms are going to be of the form a times b, where we start with a to the n and b to the 0. And as we go down our list of terms, we decrease the power of a by 1 and increase the power of b by 1 until we get to a to the 0, b to the n. And we say that the coefficients of this expanded binomial are these combinations. And a combination is the number of ways we can take a smaller group of numbers from a larger group of numbers. Now, the larger group of numbers that we're talking about taking our smaller group of numbers from is going to correspond to the power that we raised our binomial to, right? And the smaller group of numbers that we're taking from that n, that power we're raising our binomial to, is basically going to correspond to the power of the b terms, right? So right here, with our first combination, we would be looking at n choose 0, or the number of ways we can choose 0 things from n things, and that would be 1, right? And this second combination would be n choose 1, or the number of ways we can choose 1 thing from n things, and that would be n, right? And as we go down, those combinations give us our coefficients for our binomial. So right here, we're going to start by talking about our f of x equals x to the n, and we are going to apply the limit definition of the derivative to this function, right? And when we do that, we get the limit as h goes to 0 of x plus h to the n minus x to the n over h. And right here, notice that our x plus h to the n is a binomial raised to the n power. And we can expand that binomial out, as we've done right here. And right here, we'll have this binomial expanded out in red, right? And then minus x to the n. Now, for some of these combinations, we're actually going to be able to evaluate the combinations for numbers without actually knowing what n is, right? When we say n choose 0, we're talking about the number of ways that we can choose 0 things from n things. And whatever n is, the number of ways we can take 0 things from n things would be 1, right? With n choose 1, we can say that we're talking about the number of ways we can take 1 thing from n. And again, whatever n is, the number of ways that we can take 1 thing from n things would be n, right? As an example, we've got down here 7 choose 1, right? And the number of ways I can take 1 of 7 things would be 7, right? And then going down our list right here, we can't really evaluate n choose 2 without knowing what n is. But we can go all the way down to n choose n and say the number of ways that we can select n things from n things would also be 1. So we would end up with a coefficient of 1 for that x to the 0, h to the n. X to the 0 is, of course, 1, so we would just end up with h to the n there. So right here, we've got some of our combinations evaluated, as many as we really need. And our next step is going to be to cancel out all of the non-h terms, right? Now, for our non-h terms, we're basically just looking at x to the n right here, and x to the n that we're subtracting away, right? And we're sort of saying that all the other terms we would have at least one h multiplied in them. We're starting out with 1h for our n times x to the n minus 1h, and then as we go down our list of terms, that power of n increases by 1 each time we go down the term, right? All the way to h to the n. So finally right here, we have a list of terms, all of which have h as a factor, and when we factor h out of each of these terms, the only term without an h in it is going to be that n times x to the n minus 1. And now right here we cancel our h in the numerator and denominator, and now we let h go to 0, and when that happens, the rest of our terms basically become 0 terms, and we get finally right here our derivative with the limit definition of the derivative as n times x to the n minus 1. Now right here, this limit definition of the derivative we can apply to anything that is x raised to some constant power. So right here we can say if we have f of x as x cubed, we would say the derivative would be 3x squared, where we are multiplying in front by that 3 and subtracting 1 in the exponent, right? If we've got x squared, we're taking the derivative of that with the power rule. We can say that right here the derivative would be that power of 2 multiplied in front, and then 2 minus 1 in the exponent, or a power of 1, right? And right here, if we look at just x, we can say that we have a power of 1 there. And if we're using the power rule, then our derivative is going to be 1 times x to the 1 minus 1, which gives us 1 times x to the 0, or right here, just 1, right? So right here, we're seeing the power rule sort of give us these derivatives that we used to have to go through all these steps to get very quickly. And we're going to sort of elaborate on this as we go through and talk about polynomials and other functions that we can represent with x's raised to powers.